Welcome to today's paper reading. Today's paper is titled, LazyLLM, Dynamic Token Pruning for Efficient Long Context LLM Inference. This paper was published on the AR14 preprint by Qichen and colleagues from Apple and Meta AI. The inference process of transformer-based large language models involves two main stages. The prefilling stage, where the KV cache for prompts is computed and the first token is generated, and the decoding stage, where subsequent tokens are generated. For long prompts, the prefilling stage can become a bottleneck due to the need to compute the KV cache for all tokens. This raises the question of whether all prompt tokens are necessary for generating the first token. To address this, the authors introduced LazyLLM, a method that selectively computes the KV cache for tokens important for the next token prediction. Unlike static pruning methods, LazyLLM allows for dynamic selection of different token subsets at each generation step. Experimental results show that LazyLLM can accelerate the prefilling stage of the Llama 2 7B model by 2.34 times in multi-document question-answering tasks without requiring fine-tuning, while maintaining accuracy. The inference process of large language models, LLMs, involves two main stages, prefilling and decoding. During prefilling, the model computes and saves the key value, KV, cache for each token from the prompt, predicting the first token. This stage is referred to as the time to first token, TTFT. The decoding stage follows, where the model iteratively generates subsequent tokens using the cached KVs. For long prompts, TTFT can be slow due to the deep and wide architecture of state-of-the-art LLMs, where the cost of computing attention increases quadratically with the number of tokens. For instance, Llama 2, with 7 billion parameters and 32 transformer layers, requires 21 times the wall time of each subsequent decoding step for TTFT. To address this, the authors propose LazyLLM, a technique that selectively computes the KV for important tokens and defers the computation of less relevant tokens. This method uses an additional caching mechanism, AUX cache, to efficiently revive pruned tokens, ensuring that the worst runtime of LazyLLM is never slower than the baseline. Figure 1 illustrates the two stages of prompt-based LLM inference, prefilling and decoding. During the prefilling stage, the model computes the KV cache for each token from the prompt and predicts the first token. This stage can be particularly slow for long prompts, as exemplified by the Llama 2 7B model, where the time to generate the first token is 21 times longer than each subsequent decoding step and constitutes 23% of the total generation time on the long benchmark. The increase in the scale of large language models, LLMs, has led to enhanced performance but also introduced challenges in inference efficiency. To address these challenges, extensive work has been done to improve inference efficiency for long context applications. This includes reducing the memory footprint and total computations, as well as tailoring the architecture of the transformer for long context input. Additionally, token pruning techniques have been developed to selectively remove less important tokens during inference, thereby minimizing computational demands. Closer to our work, efficient techniques have been proposed to optimize the KV cache by minimizing its size and data transfer. However, these methods primarily focus on accelerating decoding steps and are not applicable to reducing the time to first token, TTFT. Figure 2 illustrates the attention scores of input tokens in the prompt with respect to the next token for each layer of the Llama 2 7B model. The distribution of the average attention score across all transformer layers is also plotted. The results show that the attention scores of input tokens with respect to the next token are very sparse, indicating that many tokens in the input prompt are redundant and can be safely removed without affecting the next token prediction. LazyLLM introduces a novel approach to optimize large language model, LLM, inference by progressively pruning tokens. This dynamic pruning strategy allows the model to select different subsets of tokens at each generation step, which is crucial for maintaining performance. The token pruning mechanism uses a top K percentile selection strategy to determine which tokens to prune based on their importance, as determined by layer-wise attention scores. Additionally, an AUX cache is introduced to store hidden states of pruned tokens, ensuring efficient retrieval without repetitive computation. This results in a significant reduction in time to first token, TTFT, and overall computation, achieving a balance between speedup and accuracy without the need for additional training. Figure 3 illustrates the difference between standard large language models, LLMs, and LazyLLM. In the prefilling stage, LazyLLM does not compute the key value, KV, cache for all input tokens. Instead, it focuses on the tokens that are crucial for predicting the next token, postponing the computation of the others until they become relevant. This selective approach significantly optimizes the time to first token, TTFT, by decreasing the computational load during prefilling. Additionally, LazyLLM ensures that some tokens in the prompt are never computed if they are not needed throughout the entire generation process, thereby further reducing the overall computational requirements and speeding up the generation process. Figure 4 illustrates the LazyLLM framework, which begins with the full context and progressively prunes tokens to reduce computational load. This dynamic pruning method allows the model to select different subsets of tokens at each generation step, optimizing next token prediction and maintaining performance. The introduction of AUX cache ensures that hidden states of pruned tokens are stored for potential reuse, minimizing repetitive computation and ensuring efficiency. In this section, we discuss the implementation details of LazyLLM. LazyLLM is implemented on two models, Llama 2 and Qichen. The evaluation is conducted on the long bench benchmark, which includes multiple datasets across various tasks. Each task is evaluated using different metrics such as RUGEL, F1, and accuracy. For inference, all experiments are performed on NVIDIA A100 GPUs. We measure two types of speedups, TTFT speedup, which is the time from prompt input to the first token generation, and generation speedup, which is the time from prompt input to the completion of all output tokens. To ensure accurate measurements, we include 5 warm-up runs before starting the time measurement. In this section, we discuss the experimental setup and key findings. We used two large language models, Llama 2 7B and Qichen 7B, and evaluated them on the long bench multitask benchmark, which includes 16 datasets across 6 tasks. The primary metrics for evaluation were TTFT speedup versus accuracy, percent of prompt token computed, and generation speedup. Our method, LazyLLM, consistently achieved better TTFT speedup with negligible accuracy drop compared to baselines. Notably, the prompt compression approach was computationally expensive and did not improve TTFT significantly. Table 1 presents the TTFT speedup versus accuracy comparisons between LazyLLM, standard LLM, and other baselines. The table shows that LazyLLM consistently achieves better TTFT speedup with negligible accuracy drop across multiple tasks. It is noted that the overhead of running LLMs to compress the prompt is very computationally expensive, making the actual TTFT of the prompt compression baseline longer than the standard baseline. Table 2 presents the percent of prompt token computed and generation speedup of LazyLLM across various tasks. The percent of prompt token computed shows variability across tasks, indicating that LazyLLM does not always utilize all tokens. Generation speedup is observed to differ significantly between Llama 2 and Qichen models. This reduction in computation by LazyLLM contributes to an overall speedup in the generation process. Figure 5 illustrates the comparison of TTFT, time to first token, speedup versus accuracy for the Llama 2 7B model across various tasks. The visualization demonstrates that LazyLLM, without any training, maintains higher accuracy than baseline methods under similar TTFT speedup conditions. For instance, LazyLLM can deliver a 2.34 times TTFT speedup in the multi-document question answering task with a negligible performance loss of less than or equal to 1%. Additionally, by adjusting pruning parameters, LazyLLM achieves a 3.0 times TTFT speedup in the same task with an accuracy degradation of less than or equal to 10%, showcasing a favorable trade-off between speed and accuracy compared to baseline methods. This figure highlights LazyLLM's efficiency and inference speed without compromising significantly on accuracy. Figure 6 illustrates the impact of pruning layers and the number of tokens pruned on model performance. It shows that both Llama 2 7b and XGen 7b exhibit similar trends. As fewer tokens are retained at the same transformer layer, model performance gradually declines. Additionally, pruning at later transformer layers consistently results in better performance compared to earlier layers, indicating that later layers are less sensitive to token pruning. Figure 7 illustrates the number of tokens processed during generation using the LazyLLM technique with Llama 2 7b. The graph shows statistics from 1,000 samples randomly selected from Longbench. The x-axis represents the generation time step, while the y-axis indicates the number of prompt tokens processed at each time step, normalized by the prompt size. The data is visualized for different stages within the network, highlighting that cumulative token usage is capped by the baseline, especially in early layers. In this study, the authors introduced a novel technique called LazyLLM, designed to enhance the efficiency of large language model (LLM) inference, especially in scenarios with long contexts. LazyLLM selectively computes key-value pairs for tokens that are crucial for predicting the next token, while deferring the computation of less relevant tokens until they become necessary. Through various tasks, the authors demonstrated that LazyLLM significantly reduces the time to first token, TTFT, without compromising performance. Importantly, this method can be easily integrated with existing transformer-based LLMs to boost their inference speed without the need for additional fine-tuning. Thank you for watching.